Hello everyone, today we'll study exponential growth and decay. First of all, let me introduce what it is. Let y represent amount of object, and let t represent time. If the rate of change of y with respect to time is proportional to its size, then dy over dt equal to r times t. So dy over dt is proportional to y. dy over dt equal to r times y. In this case, we say y grows or decays exponentially. If we solve the above differential equation, this is a differential equation. In this equation, it contains derivative. This is called a differential equation. If we solve this differential equation, what do we get? If we solve this differential equation, we have dy over dt equal to r times y. This is a differential equation. If we try to solve this differential equation, we can try to bring y to the left side. So I can first of all divide both sides by y. I get 1 over y on the left side. Next, we can try to move t to the right side. So I can multiply both sides by dt. So I get 1 over y dy equal to r times dt. I first of all divide both sides by y, and then multiply both sides by dt. So I get 1 over y times dy equal to r times dt. Next, take integral on both sides. Take integral on both sides. I get integral of 1 over y dy equal to integral of r dt. Next, take antiderivative on both sides. On the left side, if I take antiderivative, I get ln of absolute root of y. On the right side, I get rt. When we take antiderivative at constant c, on the right side here, treat r as a constant. Take antiderivative with respect to t, I get rt plus c. Next, try to solve the equation, get y by itself. In order to get y by itself, I need to first of all eliminate ln. So apply e on both sides. I get e to the power of ln of absolute value of y equal to e to the power of rt plus c. Now, on the left side, e and ln, they are inverse function of each other. They get cancelled. We get absolute value of y. On the right side, by law of exponents, it can be rewritten as e to the power of rt times e to the power of c. Next, we try to get y by itself. If absolute value of y equal to this expression, that means y itself could be either positive or negative, e to the power of rt times ec. If absolute root of y equal to this expression, that means y by itself could be either positive or negative of this expression. Next, e to the power of c, that's a constant. Since c is a constant, e to the power of c is a constant. I can bring the constant to the front. I get y equal to plus or minus e to the power of c times e to the power of rt. Then, if I let this is a constant, plus or minus e to the power of c, this is a constant. If I let y sub 0 equal to plus or minus e to the power of c, if this is a constant, plus or minus e to the power of c, that's a constant. If I let y sub 0 equal to plus or minus e to the power of c, this equation can be rewritten as y equal to y sub 0 e to the power of rt. This is y sub 0 times e to the power of rt. Now in this function here, y0 is a constant, r is a constant, the only variable is t. So I treat y as a function of t. Right? Y of t equal to y sub 0 times e to the power of rt. So if I solve this differential equation, I get y of t equal to y sub 0 times e to the power of rt. So here, if I solve this differential equation, I get y of t equal to y sub 0 times e to the power of rt. And in this equation, y represents amount of object, t represents time, y sub 0 represents the initial amount of an object, t represents time, r represents the relative growth rate or decay rate of an object. Y of t represents the amount of an object after the time period t. Next, let me show you some examples of exponential growth or decay. In general, population growth or continuously compound interest, they can be considered as exponential growth. And value depreciation and radioactive decay, they can be considered as exponential decay. Next, let me show you some examples. First example, a bacteria culture has an initial population of 100. An hour later, it grows to 150. Assume the population of the bacteria grows exponentially. Part A, find the population after 1 hour 20 minutes. Part B, find the rate of growth after 2 hours. Part C, how long will it take the bacteria to grow to 1 million? So, before we answer these questions, let's write down the formula first. For exponential growth or decay, the formula is y of t equal to y sub 0 times e to the power of rt. Then, based on this formula, write down the given information. What's given is that the initial population is 100. That means y sub 0 is 100. And 1 hour later, the population grows to 150. That means the population after 1 hour is 150. Now, in general, in this formula, if the growth rate is not given, we must find the growth rate first. If r is not given, we must find r first. So let's find r. Let's use the given information, find r. We know that y of 1 is 150. If I plug in 1 for t, what do we get here? If I plug in 1 for t, I get y of 1 equal to y sub 0 times e to the power of r times 1, which is r. Next, we know y of 1 is 150. Plug in here. Y sub 0 is 100 times e to the power of r. Next, solve an equation for r. I can divide both sides by 100 here. I can divide both sides by 100. If I divide both sides by 100, I get e to the power of r equal to 150 over 100, which is 3/2. In general, we don't have to get r by itself. Leave it as e to the power of r should be okay. We don't have to get we don't have to get r by itself. Leave it as e to the power of r is okay. Now, based on this information here, rewrite the formula. Based on this information here, rewrite the formula. Y of t is y sub 0 times e to the power of rt. E to the power of rt, by the law of exponent, it can be rewrite as e to the power of r raised to the power of t. Then plug in the given information. Y sub 0 is 100. E to the power of r is 3/2. So that's the simplified formula. Next, based on this formula, answer the questions A, B, and C. Let's answer part A first. Find the population after 1 hour 20 minutes. Here, time is 1 hour 20 minutes. 1 hour 20 minutes is 1 1/3 hours. 1 hour 20 minutes is 1 1/3 hours, which is 4/3. 1 1/3 can be rewritten as 4/3. Then in part A, t is 4/3. We're looking for the population after 1 hour 20 minutes. So by plugging 4/3 for t, we can find the population. So in part A, we plug in 4/3 for t. We can find the population after this time period. So that's 100 times 3/2 to the power of 4/3. Then here is my calculator. It's about 171.7. And usually for number of bacteria, round to the nearest whole number, it's about 172 bacteria. Let's answer to part A. Part B. Find the rate of growth after 2 hours. The rate of change is the derivative. the rate of change is the derivative. So for part B, we take derivative, then plug in 2. Take derivative, then plug in 2. That's y of t. Y of t is 100 times 3/2 to the power of t. If I take derivative, what do we get here? If we take derivative, 100 is a constant. It's a constant multiple. It stays the same. And when we take derivative for a to the power of x, the derivative is ln of the base times the function itself. So here the base is 3/2. When we take derivative, I have ln of 3/2 times the function itself. 3/2 to the power of t. Then for the rate of growth after 2 hours, I plug in 2 for t. I get 100 times ln of 3/2 times 3/2 to the power of 2. Then use calculator. Here I get 91.23. So it's about 91.23 bacteria per hour. So the growth rate after 2 hours is about 91.23 bacteria per hour. Part C. How long will it take the bacteria to grow to 1 million? How long will it take the bacteria to grow to 1 million? So in part B, we're looking for a time such that y of t is 1 million. We're looking for the time such that y of t is 1 million. So plug in 1 million for y of t and solve the equation for t. I get 1 million equal to 100 times 3/2 to the power of t. Then solve the equation for t. Here I can first of all divide both sides by 100. If I divide both sides by 100, I get 10,000 equal to 3/2 to the power of t. Next, I can apply ln to both sides. I get ln of 10,000 equal to ln of 3/2 to the power of t. Then, by the law of exponent, by the law of logarithm, I can bring t to the front. I get ln of 10,000 equal to t times ln of 3/2. Then solve the equation for t. I divide both sides by ln of 3/2. I get ln of 10,000 divided by ln of 3/2. Then use calculator. I get 22.72 on the calculator. So it's about 22.72 hours. The unit is hour. It takes about 22.72 hours. So the population will grow to 1 million in 22.72 hours. Next example. Consider investment whose value grows exponentially. Assume the value of the investment doubles every 15 years. Part A. What's the annual growth rate? Part B. How long will it take the investment to triple its value? So, before we answer this question, let's write down the formula first. The formula is y of t equal to y sub 0 times e to the power of rt. Then, write down the given information. Based on this formula, write down the given information. We know that the value doubles every 15 years, which means the value after 15 years is twice of the initial. The value after 15 years is twice of the initial. That's what's given. Now, if r is not given, we need to use the given information, find r first. In general, if r is not given, we need to use the given information, find r first. How can we find r here? We know that y15 is 2 times y sub 0. So let's first of all plug in 15 for t. If we plug in 15 for t, I get y of 15 is y sub 0 times e to the power of r times 15. we know that y of 15 is 2y sub 0. Next, I can divide both sides by y sub 0. I can divide both sides by y sub 0. If I divide both sides by y sub 0, I get 2 equal to e to the power of r times 15. Next, I try to eliminate 15. I try to eliminate power 15 here. In order to eliminate 15, I raise both sides to the power of 1 over 15. In order to eliminate 15 here, I raise both sides to the power of 1 over 15. Then left side is 2 to the power of 1 over 15. On the right side, by the law of exponents, I multiply 15 to r times 15. I get r by itself. Here I get r. I get e to the power of r. In general, we can leave it as e to the power of r. We don't have to get r by itself. But in this particular question, part A, the question is asking what's the annually growth rate. That means in part A, we are looking for r. If we are looking for r, then we must get r by itself. So for part A, I apply ln to both sides. Apply ln to both sides. I get ln of 2 to the power of 1 over 15 equal to ln of e to the power of r. Then, on the right side, ln cancels e, I get r by itself. On the left side, I can bring 1 over 15 to the front. I get 1 over 15 times ln of 2. Then use calculator. Take 1 over 15 times ln of 2. In my calculator, I get 0.0462. Then write it as a percent. I get 4.62%. That's the annually growth rate. That's the annually growth rate. That's the answer to part A. Part B. How long will it take the investment to triple its value? So, in order to answer part B, let's plug e to the power of r into the formula and simplify the formula first. In order to answer part B, let's plug in e to the power of r. Simplify the formula first. So in part B, if I plug in e to the power of r into the function here, the function y of t equal to y sub 0 times e to the power of rt, that can be rewritten as e to the power of r to the power of t. We don't know y sub 0, so leave it the way it is. But we know e to the power of r is 2 to the power of 1 over 15. Then raise to the power of t. Next, by the law of exponents, I can multiply the exponents. I get 2 to the power of t over 15. Here I get 2 to the power of t over 15. Next, we try to find out how long will it take the investment to triple its value. So in part B, we are looking for time such that y of t equal to the triple of the initial. We are looking for t such that y of t equal to the triple of the initial. So plug in 3y sub 0 for y of t. Solve an equation for t. So I have 3y sub 0. Plug in 3y sub 0 here for y of t equal to y sub 0 times e to the power of t over 15. Then solve this equation for t. Solve this equation for t. I can first of all divide both sides by y0. If I divide both sides by y0 get cancelled. We get 3 equal to 2 to the power of t over 15. In order to solve for t, I can apply ln to both sides. I get ln of 3 equal to ln of 2 to the power of t over 15. Then, by the law of logarithm, I can bring exponent to the front. I get ln of 3 equal to t over 15 times ln of 2. In order to solve for t, I can first of all multiply both sides by 15 I get 15 ln of 3 equal to t times ln of 2. Next, I can divide both sides by ln of 2. T equal to 15 ln of 3 over ln of 2. Then use calculator. 15 ln of 3 over ln of 2. In my calculator, I get 22.78 years. So it takes 22.78 years to triple its value. Next example, the value of a car depreciates exponentially. Assume it depreciates to 90% of its original value in a year. How long will it take the car to depreciate to 60% of its original value? So, for exponential growth or decay, let's first of all write down a formula. Y of t is y sub 0 times e to the power of rt. And then write down the given information. It depreciates to 90% of its original value in a year. So that means after 1 year, its value is 90% of the original value. And 90% can be rewritten as 0.9. So y of 1 is 0.9 times y sub 0. That's the given information. Now, we know y of 1 is 0.9 times y sub 0. If I plug in 1 for t, what do we get here? If I plug in 1 for t, what do we get here? If I plug in 1 for t, I get y sub 1 equal to y sub 0 times e to the power of r times t, which means r times 1, that's r. So first of all, since y of 1 is given, we plug in 1 for t. Then plug in the value. Here we know that y of 1 is 0.9 times y sub 0. Next, we can divide both sides by y sub 0. Next, I can divide both sides by y sub 0. If I divide both sides by y sub 0, I get 0.9 equal to e to the power of r. In general, we don't have to get r by itself. Leave it as e to the power of r is okay. Now, based on this information here, rewrite the formula. Based on this information here, rewrite the formula. We know that y of t is y sub 0 times e to the power of rt. By the law of exponents, e to the power of rt can be rewritten as e to the power of r to the power of t. Then plug in e to the power of r is 0.9. So I get y of t equal to y sub 0 times 0.9 to the power of t. That's the simplified formula. Now, based on the simplified formula, answer this question here. How long will it take the car to depreciate to 60% of its original value? So, we're looking for time such that y of t is 60% of the original. We're looking for t such that y of t is 60% of an original value. And 60% of y sub 0 can be rewritten as y of t equal to 0.6 times y sub 0. Now, plug in y sub 0 here. Solve an equation for t. Plug in y sub 0 here. Plug in y of t here. Solve an equation for t. If I plug in 0.6 y sub 0 for y of t, I get 0.6 y sub 0 equal to y sub 0 times 0.9 to the power of t. Now, in this equation, on the left side and right side, they both contain y sub 0. So I can divide both sides by y sub 0. If I divide both sides by y sub 0, they get cancelled. I get 0.6 equal to 0.9 to the power of t. So divide both sides by y sub 0, I get 0.6 equal to 0.9 to the power of t. Next, solve an equation for t. I can apply ln to both sides. I get ln of 0.6 equal to ln of 0.9 to the power of t. Then by law of logarithm, I can bring t to the front. I get ln of 0.6 equal to t times ln of 0.9. Next, I can divide both sides by ln of 0.9 and get t by itself. So t is ln of 0.6 divided by ln of 0.9. Then here I use my calculator. ln of 0.6 divided by ln of 0.9 in my calculator is about 4.85. So it takes about 4.85 years. It takes about 4.85 years to depreciate to 60% of its original value. Next example, a sample of a special chemical has an initial mass of 200 grams. Assume it decays exponentially and decays to 120 grams in 90 days. Part A, find its half-life. Part B, how long will it take the chemical to decay to 1 gram? So, before we answer this question, let's write down the formula first. Let's first of all write down the formula for exponential growth or decay. For exponential growth or decay, the formula is y of t equal to y sub 0 times e to the power of rt. Next, write down the given information. What's given is that the initial mass is 200 grams. So y sub 0 is 200. And it decays exponentially. It decays to 120 grams in 90 days. That means the mass after 90 days is 120 grams. The mass after 90 days is 120 grams. So that's what's given. In general, if R is not given, if the growth rate or decay rate R is not given, we must find R first. Here we know that y of 90 is 120. So let's first of all plug in 90 for t. We know y of 90 is 120. Let's first of all plug in 90 for t. If I plug in 90 for t, I get y of 90 equal to y sub 0 times e to the power of r times 90. If I plug in 90 for t, that's what I get here. Next, plug in the values. Y of 90 is 120. Y sub 0 is 200 times e to the power of r times 90. Next, I can divide both sides by 200. If I divide both sides by 200, on the right side, I get e to the power of r times 90. On the left side, I get 120 over 200. 120 over 200 can be reduced as 3/5. 120 over 200 can be reduced as 3/5. Next, we try to eliminate 90, get e to the power of r by itself. Next, try to eliminate 90, get e to the power of r by itself. So I can raise both sides to the power of 1 over 90. Raise both sides to the power of 1 over 90. Then, on the left side, I get 3/5 to the power of 1 over 90. On the right side, by the law of exponents, I multiply the exponent here. R times 90 times 1 over 90 is R. I get e to the power of r. So here we get e to the power of r is 3/5 to the power of 1 over 90. In general, we can leave it the way it is. We don't have to get r by itself. We don't have to get r by itself. We can leave it like the way it is. Now, use this information here. Simplify the formula. Use this information here. Simplify the formula. Y of t is y sub 0 times e to the power of rt. E to the power of rt can be rewritten as e to the power of r to the power of t. We know that y sub 0 is 200. E to the power of r is 3/5 to the power of 1 over 90. Then, by the law of exponents, I can multiply exponent here. 1 over 90 times t is t over 90. So y of t is 200 times 3/5 to the power of t over 90. That's the simplified formula. Now, based on this formula, let's answer the question for part A and part B. Let me copy the formula, put it here. Y of t is 200 times 3/5 to the power of t over 90. Now, part A, we're looking for the half-life. Half-life is time. We're looking for the time such that the mass after this time period is half of the initial. That's called half-life. Half-life is a time period such that the mass after this time period is half of the initial mass. And we know that initial mass is 200. Half times 200 is 100. So plugging y of t, I get 100 equal to 200 times 3/5 to the power of t over 90. Then solve the equation for t. Here I can first of all divide both sides by 200. If I divide both sides by 200, on the right side I get 3/5 to the power of t over 90. On the left side, I get 100 over 200. 100 over 200 is a half. Now, solve the equation for t. I can first of all apply ln to both sides. I get ln of half equal to ln of 3/5 to the power of t over 90. Next, by the law of logarithm, I can bring exponent to the front. I get ln of half equal to t over 90 times ln of 3/5. Next, in order to solve for t, I can first of all multiply both sides by 90. I get 90 ln of half equal to t times ln of 3/5. Next, in order to get t by itself, I can divide both sides by ln of 3/5. So I get t equal to 90 ln of half over ln of 3/5. Then its calculator. Take 90 times ln of half over ln of 3/5. Use calculator, I get 122.12. And here, t is measured in days. So we take 122.12 days to decay to half of the initial mass. So the half-life is about 122.12 days. So the half-life of this chemical is about 122.12 days. Part B. How long will it take the chemical to decay to 1 gram? How long will it take the chemical to decay to 1 gram? So for part D, again, we're looking for time such that y of t, the mass after this time period, is 1 gram. So for part B, we're looking for time such that after this time period, the mass is 1 gram. So very similar. We plug in 1 for y of t. We plug in 1 for y of t. Then solve an equation for t. If I plug in 1 for y of t, I get 1 equal to 200 times 3/5 to the power of t over 90. Then solve the equation for t. I can first of all divide both sides by 200. So I get 1 over 200 equal to 3/5 to the power of t over 90. Next, I can apply ln to both sides. ln of 1 over 200 equal to ln of 3/5 to the power of t over 90. Next, by the law of logarithm, we can bring exponent to the front. I get ln of 1 over 200 equal to t over 90 times ln of 3/5. Next, in order to solve for t, I can multiply both sides by 90. If I multiply both sides by 90, I get 90 times ln of 1 over 200 equal to t times ln of 3/5. Then next, I can divide both sides by ln of 3/5. I get t by itself. So t is 90 times ln of 1 over 200 over ln of 3/5. Then use calculator. 90 times ln of 1 over 200 over ln of 3/5. In my calculator, I get 933.49. The unit is days. So it takes 933.49 days to decay to 1 gram. Next example, a cup of hot coffee with a temperature of 200 degrees Fahrenheit is put on a table inside a room. Assume the room temperature is about 75 degrees Fahrenheit, and the temperature of the coffee decreases to 180 degrees Fahrenheit in 10 minutes. Part A, what will the temperature of the coffee be in 20 minutes? Part B, how long will it take the temperature of the coffee to be 150 degrees Fahrenheit? According to physics, we know that the temperature also changes exponentially. In order to apply exponential growth or decay for temperature, we must use relative temperature. That's the only difference. In order to apply exponential growth or decay for temperature, we must use relative temperature. Relative temperature is real temperature minus surrounding temperature of an object. Relative temperature of an object is always real temperature of an object minus the surrounding temperature of an object. Relative temperature is always the real temperature minus the surrounding temperature. So let's make a table for the relative temperature and the surrounding temperature. For the relative temperature and the real temperature. In this problem, what's the surrounding temperature? Since the coffee is put in a table inside a room, and the room temperature is 75 degrees Fahrenheit, so this is the surrounding temperature. That's the temperature surrounding the coffee. So in this problem, surrounding temperature is 75 degrees Fahrenheit. In this problem, the surrounding temperature is 75 degrees Fahrenheit. Now, in order to apply exponential growth or decay for temperature, we must change all real temperature to relative temperature. So, the coffee has a temperature of 200 degrees Fahrenheit. That's the real temperature. If we try to change real temperature to relative temperature, we take real temperature minus the surrounding temperature. Here, surrounding temperature is 75 degrees, so take 200 minus 75, which is 125. Another real temperature is 180 degrees. Another real temperature is 180 degrees. So for relative temperature of 180, I take real temperature minus the surrounding temperature. 180 minus 75 is 105. So for 200 degrees Fahrenheit, its relative temperature is 125 degrees. For 180 degrees Fahrenheit, its relative temperature is 105 degrees. What does this number mean? What do they mean? 125, it means for real temperature 200 degrees, it's 125 degrees above the surrounding temperature. 125, it means for the real temperature 200 degrees, it's 125 above the surrounding temperature. For 180 degree, it means the relative temperature 105, it means 180 degree is 105 degree above the surrounding temperature. This number 125 means 200 degree is 125 degree above the surrounding temperature. 105 means 180 degree is 105 degree above the surrounding temperature. Now, once we find the relative temperatures, we can apply the formula for exponential growth or decay. Y of t is y0 times e to the power of rt. In this formula, we can only use relative temperature. We cannot apply real temperature in this formula. We must apply relative temperature in this formula. Now, write down what's given. The coffee has initial temperature of 200 degrees Fahrenheit. So the initial temperature is 200 degrees Fahrenheit. For 200 degrees Fahrenheit, its relative temperature is 125 degrees. That's an initial temperature. Initial temperature is 200 degrees. That means it's 125 degrees above the surrounding temperature. Then we know that 10 minutes later, the temperature decreased to 180 degrees. 10 minutes later, the temperature decreased to 180 degrees. And for 180 degrees, its relative temperature is 105 degrees. For 180 degrees, its relative temperature is 105 degrees. So the temperature after 10 minutes is 185, it's 105 degrees. This is the relative temperature of 180. In the formula for exponential growth or decay, we must use relative temperature. We cannot use real temperature in this formula. Now, if R is not given, let's find R first. If R is not given, let's find R first. We know that y of 10 is 105. So let's first of all plug in 10 for t. I get y of 10 is y sub 0 times e to the power of r times 10. Then plug in numbers. We know y of 10 is 105. y0 is 125 times e to the power of r times 10. Next, I can divide both sides by 125. If I divide both sides by 125, on the left side, on the right side, I get e to the power of r times 10. On the left side, I get 105 over 125. 105 over 125, if I use calculator, that's 21 over 25. For 105 over 125, I get 21 over 25. Next, we try to eliminate 10, get e to the power of r by itself. In order to eliminate 10, I raise both sides to the power of 1 over 10. I raise both sides to the power of 1 over 10. Then, on the left side, I get 21 over 25 to the power of 1 over 10. On the right side, by the law of exponents, I multiply exponent here. R times 10 times 1 over 10 is R. I get e to the power of r. Next, plug in e to the power of r. Rewrite the formula. Y of t is y sub 0 times e to the power of r to the power of t. We know that y sub 0 is 125. E to the power of r is 21 over 25 to the power of 1 over 10. Raised to power of t. Next, by the law of exponent, I multiply 1 over 10 times t. I get y of t equal to 125 times 21 over 25 to the power of t over 10. So that's the simplified formula. Now, based on this formula, answer the question. Part A. what would the temperature of the coffee be in 20 minutes? So we're looking for temperature of the coffee in 20 minutes. We're looking for the temperature of the coffee in 20 minutes. That means I plug in 20 for T. I plug in 20 for T. We're looking for the temperature of the temperature of the coffee in 20 minutes. So time is 20. We plug in 20 for T. For y of 20, I plug in 20 for T. That's 125 times 21 over 25 to the power of 20 over 10. 20 over 10 is 2. If I plug in 20 for T, 20 over 10 is 2. 20 over 10 is 2. Then use calculator. 125 times 21 over 25 to the power of 2. In my calculator, I get 88.2 degrees. And remember, in this formula, all we get is the relative temperature. This is the relative temperature. This is the relative temperature. But in the problem, we're looking for the real temperature. We're looking for the real temperature of the coffee. This temperature, 88.2, it means 88.2 degrees above the surrounding temperature. This temperature, 88.2 here, it means 88.2 above the surrounding temperature. This temperature, 88.2 here, it means 88.2 degrees above the surrounding temperature. So the real temperature, for the real temperature, since relative temperature equal to the real temperature minus the surrounding temperature, if we try to find the real temperature, we can take relative temperature plus the surrounding temperature. So I take 88.2 plus 75. The real temperature here is 163.2 degrees Fahrenheit. That's the temperature of the coffee in 20 minutes. In order to change relative temperature back to real temperature, we take relative temperature plus the surrounding temperature. That's the real temperature of the coffee in 20 minutes. That's an answer to part A. Part B. How long will it take the temperature of the coffee to be 150 degrees Fahrenheit? 150 degrees, that's a real temperature. In order to apply this formula, we must use relative temperature. So 150 degrees minus surrounding temperature. Real temperature minus surrounding temperature will be the relative temperature. Here take 150 minus 75. 150 minus 75 is 75 degrees. So that means 150 is 75 degrees above the surrounding temperature. 150 degrees is 75 degrees above the surrounding temperature. So in part B, we're looking for time such that y of t is 75 degrees, such that the temperature after this time period is 75 degrees. Here we use relative temperature. In this formula, we can only use relative temperature. Now, here, plug in y of t is 75. Plug in 75 for y of t. Solve an equation for t. Plug in 75 for y of t. Solve an equation for t. If I plug in 75 for y of t, I get 75 equal to 125 times 21 over 25 to the power of t over 10. Then I can divide both sides by 125. I can first of all divide both sides by 125. If I divide both sides by 125, on the right side I get 21 over 25 to the power of t over 10. On the left side I get 75 over 125. 75 over 125 can be reduced as 3/5. 75 over 125 can be reduced as 3/5. Next, I'm going to solve an equation for t. apply ln to both sides. I get ln of 3/5 equal to ln of 21 over 25 to the power of t over 10. Next, by the law of exponent, I can bring exponent to the front. Sorry, by the law of logarithm, I can bring exponent to the front. I get ln of 3/5 equal to t over 10 times ln of 21 over 25. Next, in order to solve for t, I can multiply both sides by 10. I get 10 ln of 3/5 equal to t times ln of 21 over 25. Finally, in order to get t by itself, I can divide both sides by ln of 21 over 25. I get 10 times ln of 3/5 over ln of 21 over 25. Then use calculator. 10 times ln of 3/5 over ln of 21 over 25 in my calculator, I get 29.30. And it's measured in minutes. So, in 29.30 minutes, the temperature of the coffee will be 150 degrees Fahrenheit. That's the answer to part B. Next example, a bottle of water is taken out from the refrigerator with an initial temperature of 35 degrees Fahrenheit. Assume the room temperature is 60 degrees Fahrenheit, and the temperature of the water raised to 45 degrees Fahrenheit in 30 minutes. Part A, what will the temperature of the water be in 40 minutes? Part B, how long will it take the water temperature to reach 50 degrees Fahrenheit? We know that temperature also changes exponentially. But in order to use exponential growth or decay for temperature, we must use relative temperature. Relative temperature is always real temperature minus the surrounding temperature. In this problem, since water is placed in a room with temperature of 60 degrees, so the surrounding temperature in this problem is 60 degrees. So the surrounding temperature in this problem is 60 degrees. And we know that relative temperature is always real temperature minus surrounding temperature. Relative temperature is always real temperature minus the surrounding temperature. In general, let's make a table for the temperatures. In the problem, we know that the real temperature of the water is 35 degrees initially. Apply the formula. Relative temperature is real temperature minus surrounding temperature. So I take 35 minus 60 degrees. 35 minus 60 is negative 25. So negative 25 means 35 degrees is 25 degrees below the surrounding temperature. This negative 25 means 35 degrees is 25 degrees below the surrounding temperature. And the temperature, another real temperature is 45 degrees. That's the temperature of the water after 30 minutes. And for the real temperature, 45 degrees, this is a real temperature. We need to change it to relative temperature. So I take real temperature minus the surrounding temperature. 45 minus 60. 45 minus 60 is negative 15. So negative 15 means 45 degree is 15 degree below the surrounding temperature. This relative temperature, it means 45 degree is 15 degree below the surrounding temperature. This 25 degree means 35 degree is 25 degree below the surrounding temperature. And this negative 15 means 45 degree is 15 degree below the surrounding temperature. Now, next, let's write down the formula for exponential growth or decay. Y of t is y sub 0 times e to the power of rt. Write down the given information. We know that the initial temperature of the water is 35 degrees Fahrenheit. In order to use this formula, we must always use relative temperature. We cannot use real temperature in this formula. We must always use relative temperature in this formula. So, initial temperature is 35 degrees. Its relative temperature is negative 25. Initial temperature is 35 degrees, but its relative temperature is negative 25. That means it's 25 degrees below the surrounding temperature. And the temperature after 30 minutes, is 45 degrees. The temperature after 30 minutes is 45 degrees. For 45 degrees, its relative temperature is negative 15. So the temperature of the water after 30 minutes is 45 degrees, which is 15 degrees below the surrounding temperature. That was given. In general, if R is not given, we need to find R first. And we know Y of 30 is negative 15. So I first of all plug in 30 for T. If I plug in 30 for T, I get Y of 30 equal to Y sub 0 times e to the power of R times 30. Next, plugging numbers. Y of 30 is negative 15. Y sub 0 is negative 25. That's the initial temperature. That's the temperature after 30 minutes. Times e to the power of R times 30. Next, I can divide both sides by negative 25. If I divide both sides by negative 25, on the right side I get e to the power of R times 30. On the left side, I take negative 15 divided by negative 25. Negative 15 divided by negative 25. Double negative is positive. 15 over 25 can be reduced as 3/5. Next, we try to eliminate 30, get R by itself. So, in order to eliminate 30 here, I can raise both sides to the power of 1 over 30. Raise both sides to the power of 1 over 30. So, on the left side, we get 3/5 to the power of 1 over 30. On the right side, by the law of exponents, we multiply exponent here. R times 30 times 1 over 30 is R. So I get e to the power of R. Next, plugging e to the power of R into the original formula. The original formula, y of t, can be rewritten as y sub 0 times e to the power of R to the power of t. We know that y sub 0 is negative 25. E to the power of R is 3 over 5 to the power of 1 over 30. All raised to the power of t. Then, by the law of exponents, I can multiply the exponent. T times 1 over 30 is t over 30. That's the simplified formula. That's the simplified formula. Next, based on this formula, answer the question. Part A, what would the temperature of the water be in 40 minutes? So part A, time is 40 minutes. We're looking for the temperature of the water after 40 minutes. So we're looking for y of 40. I plug in 40 for t. In this formula, plug in 40 for t. I get negative 25 times 3/5. If I plug in 40 for t, 40 over 30 is 4/3. If I plug in 40 for t, 40 over 30 is 4/3. So I get negative 25 times 3/5 to the power of 4/3. Then use calculator. I type this to my calculator. I get negative 12.65. I get negative 12.65. This is the relative temperature after 40 minutes. This is the relative temperature after 40 minutes. This is the relative temperature after 40 minutes. This number, it means the temperature after 40 minutes is 12.65 below the surrounding temperature. This number, it means the temperature of the water after 40 minutes is 12.65 below the surrounding temperature. So this is the relative temperature. If we try to find real temperature, I can take relative temperature plus the surrounding temperature. If we try to find real temperature, I can take relative temperature plus the surrounding temperature. So for real temperature, I take the relative temperature plus the surrounding temperature. Surrounding temperature is 60 degrees. Together, I get 47.35 degree Fahrenheit. That means the water temperature after 40 minutes is 47.35 degrees Fahrenheit. So the temperature of the water after 40 minutes is 47.35 degrees Fahrenheit. That's the answer to part A. So for real temperature, always use relative temperature plus the surrounding temperature. For real temperature, always use relative temperature plus the surrounding temperature. That's the answer to part A. For part B, how long will it take the water temperature to reach 50 degrees Fahrenheit? So part B, we're looking for that. How long will it take the water temperature to reach 50 degrees Fahrenheit? Now, this 50 degrees Fahrenheit is a real temperature. This 50 degrees Fahrenheit is a real temperature. If we try to find the relative temperature for 50 degrees, we take real temperature minus the surrounding temperature. Take 50 minus 60. 60 is the surrounding temperature. So I take 50 degrees minus the surrounding temperature. 50 minus 60 is negative 10, which means 50 degrees is 10 degrees below the surrounding temperature. This 50 is 10 degrees below the surrounding temperature. So for part B, we're looking for time such that y of t is 50 degrees Fahrenheit. Y of t is 50 degrees Fahrenheit. And for 50 degrees Fahrenheit, its relative temperature is negative 10 degrees. So we plug in y of t here, solve an equation for t. Plug in y of t here, solve an equation for t. If I plug in negative 10, I get negative 10 equal to negative 25 times 3/5 to the power of t over 30. So I can first of all divide both sides by negative 25. If I divide both sides by negative 25, double negative is positive. 10 over 25 is 2/5. So I get 2/5 equal to 3/5 to the power of t over 30. Next, in order to solve an equation for t, I can apply ln to both sides. I get ln of 2/5 equal to ln of 3/5 to the power of t over 30. Then, by the law of exponent, by the law of logarithm, we can bring exponent to the front. I get ln of 2/5 equal to t over 30 times ln of 3/5. Next, in order to solve for t, I can first of all multiply both sides by 30. I get 30 ln of 2/5 equal to t times ln of 3/5. In order to solve an equation for t, I can divide both sides by ln of 3/5. In order to solve an equation for t, I can divide both sides by ln of 3/5. So t equal to 30 ln of 2/5 divided by ln of 3/5. Then use calculator. Then use calculator for this. In my calculator, I get 53.81. And here the time is measured in minutes. So after 50.381 minutes, the water temperature will reach 50 degrees Fahrenheit. That's the answer to part B.